welcome. Today is the first of the invited lectures of the week. And it's Kevin Buzzard who's going to, once he's got the right slide on the screen, teach number theory computers. Kevin.
Hello, thank you very much for coming. And I'm not really an ants person, so thank you very much for giving me the opportunity to be able to speak here. And I don't need a mic, right? Okay. So I'm going to give a talk. It is an hour. It's probably less than an hour. So feel free to butt in with questions. That's fine. So I'm going to talk about some software. I'll give a demo and I'll talk about what we've been doing with it recently, and then I'll give an overview. This is not a technical talk. This is pretty easy going. So what am I going to talk about? As everyone in the room is aware, you can use a computer to compute stuff. For example, like class groups of number fields. Yeah, and furthermore, amongst the stuff you can compute, there are really interesting things like class groups of number fields. And nowadays we can use computers. I'm so pleased that Henri Cohen is here. One of the first people to use computers to compute interesting stuff that I found interesting, as a number theory researcher. So here's a random stupid fact. Last year, a group of 4 people, including one of whom is my PhD student, Ashwini Narayanan, they used a computer to prove that class groups of number fields were finite, which is different to computing them, right? So that's sort of funny. And furthermore, when they finished proving it, they submitted it to some very prestigious computer science conference proceedings and got it accepted. So that's a completely something that 5 years ago I had no idea about. Like you can write computer code that proves something that Gauss knew, and then you can get it published in like the most prestigious place in the area. And this was one of the I realized I'd sort of found a gap in the market when I discovered this. So there's, you can the link is just to archive. I'm assuming that somebody will ask me for my slides afterwards, so I put links in. Let me show you. There we go. This is API documentation for a computer program called Lee. And yeah, so if you imagine looking at the analogous thing on Sage or something, it would say, here are programs which you can run, and they eat a number field and they produce a class number. So we have the same sort of things, right? That's a function, number field dot class number. And it will eat a number field and it will spit out a number. But I mean, the thing that came out, it would be called n, and you could say, is n a number? And it would say, sure. And then you could say, what number is it? And it would, I don't know. It's just like, I know you've defined it and it's a number. So it's not the same as Sage, it's doing something else. There we go. So it's doing something different. One of the things you can do is for example, you can prove, this theorem says that if the integers of your number field are a principal ideal domain, then the class number is 1. And so this theorem says the class number of Q is 1. So you could ask it what the class number of Q is, and it was, you could define n to be the class number of Q, and then you can't evaluate n, but you can still prove that n is equal to 1. Using that theorem there. So it's slightly weird. So that's what I'm gonna give a talk about, that sort of thing. So in fact, we could do even better than class numbers 1. Apparently last week, they said this is state of the art, right? State of the art. The class number of Q minus 5 is 2. It's completely ridiculous. So let's do a simpler example. Let me actually show you the software working. I'm not going to start going into class groups. But let's just do prime numbers, which are perhaps less interesting objects. But you can write a little loop that prints out a bunch of prime numbers. But my claim is you can also write computer code that will prove there's infinitely many prime numbers. So let me see if I can. Let me see if I can do that now. Let's go here. Here we are. Now then, can we see? Is that all right for those at the back? I can go bigger if you like. So I need to, so right now the system knows the axioms of mathematics, but it doesn't know any mathematics. So we should import the definition of a prime number. And import data.mat.prime. There we go. So now the system knows what a prime number is and lots of basic maths about primes. I can show you the main function that I've just imported, nat.prime. Let's take a look at, does that exist? Yes. There you go, nat.prime. So this is the function that we now have that we didn't have before. And we've got a bunch of API for this function as well. So nat.prime is a function that eats a natural number and it returns a true-false statement. It returns a proposition. That's not a proposition in the sense of like better than a lemma, but not as good as a theorem. This is proposition in the sense of logic. This is, you know, it's a true-false statement. So I don't know. So for example, I could check nat.prime 7. Nat.prime. The computer is telling us that nat.prime 7 is the statement that 7 is prime. It's not claiming that this statement is true. I mean, I could just check. I mean, this is the statement. Oops. Oh, that was interesting. That's just the statement that 8 is prime. And that statement would be you wouldn't be able to prove that statement, but you would be able to prove. Example. Let me just prove it. Nat.prime 7. Begin end. Here we are. So now this is I mean, I think of this thing as a computer game, right? So now we're playing a computer game, and the goal of the computer game is to prove that 7 is prime. And I mean, you can imagine there's a whole bunch of proofs. Yeah, we could check it's not a multiple of 2, 3, or 4. I mean, that's not. I mean, there's ultimate. Let's see if this works. Yeah, there we go. So I just proved that 7 is prime by using an algorithm that was designed to prove that numbers are prime. And if I try and prove that 8 is prime using the same strategy, yeah, now I've got to. So now it says you're done if you can prove that 0 equals 1. You're in a bad situation when you have no hypotheses and you're trying to prove a false thing. So that's what this thing looks like. So I'm supposed to prove there's infinitely many primes. So let's get back to that. So what would that look like? Example, I claim that for all natural numbers n, there exists a p such that p is prime, and furthermore, let's have n less than root of p. Is that the same as it? Yeah, that would work, right? Begin. Oh, let me do it the other way. N less than root of p, and nat dot prime p. There we go. Begin n. Right. So now again, that bit was me making the level, and now we get to play the level. So on the right hand side of the screen, we see Lee's brain, which right now knows nothing. Let's do intro n. That line says let n be an arbitrary natural number. That first line here. I'm going to type code here in a programming language that you might not be able to follow. But over here, this is the current state. This is the current state of the game, right? And right now we have n, a natural number. We know nothing about n other than the fact it's a natural number. I mean, it's not like secretly 23 or anything. It's like a variable natural number. And we're trying to prove that there exists p such that n is at least p and p is prime.
So how did it know this n was a natural number?
Oh, the unification system works it out. Nat.prime p eats a natural number, so it figured that p was prime, and then I said that n was sorry, it figured out that p must be natural, and then it saw n was less than or equal to p, and so it realised that n had to be a natural number as well, because less than or equals to eats 2 terms of the same type. So I mean, I could have done this. Then I could have explicitly told this, but I just thought this looked cooler, right? This isn't a talk. This is just an advert, right? And I just thought that Anyway,
it's not aware of say 1/2 being less than.
No, because that doesn't even make sense. I mean, I could say 1/2 is not equal to the rational number 3. That would make sense. But Lean has got lots of different 3s. Yeah, infinitely many threes. It's got the p-adic numbers. Every one of those p-adic numbers has got a different three. So where's this p going to come from? I'm going to take the smallest prime factor of n factorial plus 1. Let's let p be, I think it's called min fac. Is that? Yeah, here we go. Min fac. This is the documentation of this function. Returns the smallest prime factor of n not equal to 1, because 1 doesn't have a smallest prime factor. And I'll put n factorial plus 1 here. And then it will say, I've never heard. Now it's complete. It doesn't know what the factorial is. So I need to put some notation on. Open locale on there. So let's try that. So let's get rid of these. This is just some. I'm enabling some notation here. And now does this work? Oh, is it nat.minfac? Let me open nat. There we go. Oh, is it? Yeah, minfac was actually called nat.minfac. So now I don't have to write nat dot. If I open nat, I can just write prime p instead of nat dot prime p. So there we go. P is the smallest prime factor of n factorial plus 1. And that's going to work, right? So let's prove it's prime. Have HP nat dot prime p. So now I'm making this claim that p is prime. So now I've got, do you see, I've got two goals now, and these goals are different. They're somehow different threads. They can't interact with each other at all now. I've got to prove that p is prime, and then I've got to prove that there exists a p which is prime and at least n. So let me do the right computer science thing. There we go. I've got two goals to now. You see now I've got one goal in that bracket and one goal in that bracket. So these are the two things. These are the two things I've got to fix. So why is p prime? I guess p is the smallest. This min fac is the smallest prime factor of something. What isn't it? Yeah. Nat dot min fac returns the smallest prime factor of something. So so now I need to apply some. There'll be a lemma that says the smallest prime factor of something is prime. And there's lots of ways of finding that lemma. The way I'm going to find it is by guessing what that lemma is called. So I'm going to apply, let me guess, min fac prime, nat dot, oh, did I open that? I did. Min fac prime, let's try. There we go, min fac prime. And now this is kind of irritating that I thought we were going to be done, but we're not done. It's now demanding that we prove that n factorial plus 1 is not 1. And the reason for that is that min fac prime, if you think about it, this is, what are we doing about 1, right? We're not running this code. This code isn't running. And yet here I'm taking the smallest prime factor of a number which sort of isn't going to be 1 in practice because factorials can't be 0. But yeah, what if it is 1? Like we could sort of step back. Yeah, we can actually we can run these functions. In fact, I don't know, if I run min, yeah, the smallest prime factor of 15 is 3. You see the output on the right there. If I do 14, the smallest prime factor. So if I run, what's the smallest prime factor of 1? It's just a jump value, it's 1. So it's the community decided that the easiest, that one nice way to make functions was let them have, if garbage in, garbage out is what's happening here, right? The smallest prime factor of a number with no smallest prime factor is just some random thing. So you see, the doc string is claiming that if n is not equal to 1, then it will return the smallest prime factor of n. And if n is equal to 1, it doesn't document what it returns. We don't care. Right? This is, you can do things like eval 1 divided by 0. You get 0. You're not supposed to divide by 0, but it's just convenience. If you demanded that the user was not allowed to divide by 0, then every time you use the division symbol, you'd have to insert a proof that the thing you were dividing by wasn't 0. And that becomes very boring very quickly. And so what happens instead is we allow the user to divide by 0, but the resulting object, there's no theorems about it in the library. So there you go. Garbage in, garbage out. So how are we let's get back to the point. How are we going to prove? I don't normally do a big live coding session, but I thought you were computer people, so I thought you might be interested. I'm going to prove that n factorial plus 1 isn't 1. So what's the maths proof? if n factorial plus 1 was equal to 1, then n factorial would be 0, and n factorial can't ever be 0 because n factorial is always positive, right? And so what's the lemma going to be called that factorials are always positive? Equals, I don't know, factorial, there it is. You see, here's all the lemmas about factorials. But you can, there, this says n factorial equals 1 if and only if n is less than or equal to 1. You've got all these random, there you go, factorial is monotonic. And this is what we want, factorial pos. Factorial, so this is a function, right? Factorial pos is a function, and it eats a natural number, and it spits out a proof. But the concept of sort of data like natural numbers and theorem statements and proofs, these are all just terms and types in this type theory system. So you can have functions which kind of eat, hello?
Is there any way of finding out if lemma is already in the system?
Yeah,
I was just guessing.
yeah, you can search. Yeah, you can, let me, so we're trying to prove that naught is bigger than n factorial, right? I'll say, I claim have foo 0 is less than n factorial, right? That's the key thing we need. And now you're asking, you know, let's say I didn't know it was going to be called factorial something. Let's just do library search, if we get lucky. There we go. So it found it for us, right? That should really, I'm writing properly in front of computer scientists, so I'm aware that I should, there we go. So now we have the proof that n factorial is positive, and so now the fact that n factorial plus 1 is not 1 is obvious, right? It's just because it's just linear inequalities. And there's a tactic that does that, linear arithmetic. So there we go. So that theorem is now proved, right? I haven't finished the proof that there's infinitely many primes, because at this point here we had 2 goals, and I've just finished the first one. Sorry means I haven't filled in the proof yet. So now we've still got this one goal left. We've got to prove that there exists a number p which is at least n and prime. And of course, what am I going to use? I'm going to use h. Let's use p. And now I've got to prove that n is less than or equal to p and p is prime. So how do you prove x and y? You prove x and you prove y, right? So if I split it again, I should have 2 goals. There we go. So, and now I've got 2. Now I've got 2. There you go. The goals divided. This is a nice easy one. I've got to prove that p is prime, but I've already proved that. So that's just exact HP. I've done that one. So the work that's left is this one here. We've got the smallest. So this is the content. This is the content of the argument in some sense. I mean, the definition of p is a brilliant idea, but then now I've got to prove. So how am I going to prove that n is less than or equal to p? I guess I'm going to prove it by contradiction. I contra HP or something. I'm trying to prove that n is less than or equal to p. So now I've got a hypothesis that p is less than n, and I'm supposed to prove something false, right? Sorry, I'm looking for now the idea is my hypothesis. You can see exactly what the hypotheses are. P is the smallest prime factor of n factorial plus 1. We know P is prime. Oh, I shouldn't call it H. I've got 2 HPs now. Call it HP. There we go. I know that P is less than n, and I know that P divides n factorial plus 1. So what's the argument? P is less than n, so P is going to divide n factorial, right? And P will also divide n factorial plus 1, so P will divide 1, and that can't happen because P is prime. So we've got to somehow put all those facts together. And now let's do that. Hello.
Question. So one thing that bothers me when I see this is how you know the definitions are correct. And then so I think my real question is this stuff, the stuff that goes into the library, is it refereed in some way?
Yeah. By the maintainers. Yeah. Who are the gatekeepers? I mean, so it's a free and public source repository, you know, and free open source software being reviewed by people like me. I mean, I'm not a maintainer of the library, but I mean, it doesn't matter if the definition of smallest prime factor is wrong, because the definition doesn't show up in the question. If at the end of this proof, you say, how do I know you proved it? I say, well, the machine says you proved it, but the thing we have to worry about is what's the definition of prime, right? That's what we have to look at. So I just right-clicked on it. So the definition of prime is, there you go, it's irreducible. What's the definition of irreducible? I mean, so it's just, you know, it's something to do with unique factorization domains or something. P is a non-unit and only factors into units. So there's some, and I guess you can see I mean, if you don't trust that definition, you see the lemmas we proved that. There we go. We proved that 0 isn't prime, that 1 isn't prime. We proved that primes are positive. We proved that primes are at least 2. We proved that primes are bigger than 1. We proved that whatever. We proved that primes aren't equal to 1. So there's evidence that, you know, there'll be. Oh, here we go. Look, we proved that if P is a prime if and only if P is at least 2, then every divisor of P is 1 or P. So the fact that that proof compiles is strong evidence that we've got the right definition.
So if you unroll the definition of prime, like how long would it something?
Oh, it's just going to say it's irreducible. Yeah, it just says I'm irreducible. And the definition of irreducible, it says else bells. It says an irreducible element of a monoid is something which is not a unit, and something that if it factors into two things, then one or other is a unit. So there you go. And of course, you can just keep going, right?
So the positive integers are monoid?
Yes, on the multiplication. Yeah, monoid is group with no inverse. We can just keep going. Right? There's the definition of unit. Units, so there we go. There. Oh, yeah. An element of a monoid is said to be a unit if there's an element in the units of the monoid such that. So M star is the units of the monoid, the invertible elements of the monoid. So yeah, you can keep it. You're absolutely right. If the definitions are wrong, then you're dead. So you have to check the definition, but you don't need to check the definitions of all the stuff I'm using here, right? You don't need to check the definition of factorial, but you do have to check the definition of prime.
How do you use the definition of M cross? Because it's not really a function of the.
Oh, that's M cross is just notation. Yeah, it's the units of a monoid. I think it's called. We could do print notation. What was it? Was it slice times or something? No. Arc X. Is it that? There we go. Yeah. It was a small Unicode S apparently, and it means units. So and then we can print units. And let's just jump to the definition. So it's a bit terrifying.
Convenient.
Yes, that. Got it. There. There's a nice constructive definition. So monoid is a group but without inverses, right? So you've got a 1 and a multiplication. And the units of a monoid. I mean, you learn the units of a ring normally. I'd never seen it applied to monoids, but every ring is a monoid. A ring is a group under addition and a monoid under multiplication. And the units of a monoid are quadruples. You see, this is another great example of, we have quadruples of objects, and the objects are not things that you would normally, like two of the objects in the quadruple are an element of alpha, another element of alpha called val and inv, and then the other two elements of the quadruple are proofs. Val times inv is 1 and inv times val is 1. So to make a term of type units alpha, you have to give a quadruple, 2 elements of alpha, and plus a proof that when you multiply them together, either way, you get the element. Are we bored? Shall I keep going? Do you want me to finish it? I spent ages on this. So just knock it off. Let's just knock it off. Have HP1. I claim that P divides N factorial. Why does P divide N factorial? It's because P is less than N, right? So rewrite. I'm just going to divide factorial. Is that a thing? Here we go. What's this? Prime dot divide factorial. That is important. Let's rewrite prime dot divide factorial. Now let's see what I've got to do. I've got to prove P is less than or equal to N. Oh, that's good. I'm going to prove P is less than or equal to N, so that's exact HPN.LE. Yeah, HPN is to prove that P is less than N, and this is very clever dot note. The type of HPN is less than, and there's something in the library called less than .LE, which is if P is less than N, then P is less than or equal to N. And you can use this funny dot note. This is less than .LE HPN. But I don't know, I think that's very cute. And now what prime P is exactly, that's just an assumption. So that's that out of the way. So P divides N factorial have HP2, P divides N factorial plus 1. Why is that true? P divides N factorial plus 1 because it's the smallest prime factor. So again, I'm going to apply, it's going to be called min fac divert or something. There it is, min fac divert. Does that work? Yeah. That was nice. I didn't have to prove that N was not equal to 1 there. Because even though the value returned is a junk value, it's still true that the minimum prime factor of 1 divides 1 equals 1. So P divides N factorial and P divides N factorial plus 1. So now I want the P divides 1. So that would be rewrite, what would that be called? At dot divert add, yeah, here we go, it'll be one of these. If K, this says if K divides N, can you see what it says? Oh, there it is. If K divides N, then K divides M, if and only if K divides M plus N. And then the other way will presumably be N plus N. Somehow, you see the N and the M are switched. So which one do I need? I've got N factorial plus 1. And so, which one?
You want to subtract, right? Not N.
Yeah, I don't want to subtract, because that's evil. Subtraction is add is right. I need to feed my proof. Let's do HP1. I don't want to. Okay, so let's go. It's the other way as well, isn't it? Let's try the other way. And now let's change the right to a left. Oh, neither of them work. Something should work. It's at HP2. And I'm going to go all the way back. Let's go back to right. Hey, finally some of them work. Right, and now I've got to prove that P divides 1. So I have the sorry, I don't. I mean, I have the I've proved that P divides 1, and now I want to prove something false. So I just need some level that says primes don't divide 1. Apply, I don't know, not divide 1 or something. Here we go. Prime. Apply. Let's try nat dot prime. Is that a thing? Not divides 1. What's this? This wants an input to prove that P is prime. So let's give it HP. Oh, bingo. And this is exact HP2. Right. So we're there. So there you go. There's a proof. There's a proof that there's infinitely many parts. Obviously, I've somehow made a meal of it on purpose, just to somehow show you what it looks like. But if you were building that, from first principles, there's a very long proof.
I have a question.
Yeah, go.
On the language. So actually, it's kind of interesting. So if you look in Euclid's elements, the way they state the primes is not what we say now. You know,
Oh, okay.
Many of them. Infinity wasn't the thing.
Oh, yeah.
Right. So he says that there's the primes are more numerous than any given quantity. So there's arbitrarily many.
Oh, okay.
Primes.
I mean, I can prove that as well if you like.
We did something similar, which is there are arbitrarily large primes. What you prove.
Yeah, I prove there's arbitrarily large primes.
Right. Is there a way of putting it that's more like what we say today? So
Yeah.
primes is infinite.
Yeah, I could absolutely do. Yeah. There'll be one. I don't want to do that live, but I mean, I'm running out of time for this. My plan is to do this until about 5:30. But yeah, sure, you can. Yeah, that's not just a carefully chosen. Actually, in some sense, it is a carefully chosen example, because another way of doing this proof is already in the library, right? I can just. Yeah, this is also a proof. There's a one-line proof. That's kind of cheating because it's already there. So what is it? I thought that I'm going to do it anyway, even though I've got overtime. Let me just tell you a little bit about what this system actually is, because you can see it's sort of a computer program, even though we don't ever run the code. We're just somehow checking that the code compiles without ever running it. So let me show you an example, just to give you a bit of an idea about what's going on. Let me prove composite of two injective functions is injective. So let's say X, Y, and Z are sets. I mean, they're not sets, they're types, right? Because this is, I mean, a type is a set. So this is type theory, and I've got a function from X to Y. I mean, you can see they're sets, right? When you say let X be a set, it's like, you tell the undergraduate, we're going to do functions F from X to Y between sets. And if an undergraduate said, well, what's a set? You'd be like, it's a collection of things. But it's just, that's exactly what a type is. A type is a set is a collection of elements. A type is a collection of terms. F from X to Y, G from Y to Z. And now let's have some hypotheses. Let's have HF, injective. Oh, I think injective is probably called function. Yeah, I've got an error on injective. Injective is called function dot injective. So let me open function. There we go. And then HG injective G. And my claim is injective G composed with F. So how are we going to prove composite of injective functions is injective? Let me fold that up. Oh yes, Patrick Massel always says I should put this thing into Zen mode. He says I'm doing the wrong thing. Let me Zen. There we go. Look. Apparently, audiences like it better when you're in Zen mode because you can't see them. Apparently, line numbers are confusing. Maybe for you people they wouldn't be. So here we are in Zen mode. And how am I going to prove? I mean, what does it even mean? I could like unfold. Let's unfold the definition of injective. Because who knows what it means, right? And you can see it means, for all A1 and A2 in X, if G of F of A1 is G of F of A2, that implies A1 is A2, right? So that's sort of, it is consistent. It is consistent with what we think injective means. So that means we can just, okay, so let's let intros A and B. Let's let A and B be elements of X. So A and B are now terms of type X or elements of the set X. Colon in type theory, B colon X means B is a term of type X. And this is the funny, this is the the weird thing that you have to get your head around, right? The A and B are data, right? They're elements of this set X. The HG is a term of type injective G, which means injective G is a statement. Injective G is the statement that G is injective, and HG is the hypothesis that G is injective, what I tell the undergraduates, but it's really a term of type injective G. So it's a proof that G is injective. And this thing here, this funny sideways T, this is a type, it's a true-false statement, and the goal is to make a term of that type. That's what we're actually doing.
That the are in X is it because you name them A and B?
No. It knows that we're trying to prove. It knows that G composed with F goes from X to Z, and so it knows we're trying to prove that for two elements of X, if G of F of X is, I mean, it's the definition of unfold. After unfold injective, it says, we've got to prove that if A1 and A2 are elements of X, then blah blah blah. And so if I let A1 and A2, or A and B, I call them, be arbitrary elements of whatever, then I will let them be elements of X.
Victoria, somehow it's guessing.
No guessing is happening.
Could you introduce an A and B there for Y right now instead if you
No, I don't understand what you mean. I'm lost. It's nothing, no guesswork is happening. It's the elaborator is working out what we mean. The goal right here is to prove that G composed with F is injective. And G composed with F is a function from X to Z. And so the goal is the statement that if we've got two elements of X and they become equal in Z, then they're equal in X.
A student might start their proof by saying let A and B be elements of Y because they're not very good students.
Yeah, so maybe we could use this to teach weak undergraduates. Unfortunately, I've discovered from raw experience that walking into your introduction to proof course and dumping this in front of the first years and saying, we're going to do math like this now, turns out that the vast majority of them go, no! It's not something that works very well. And I'm somehow still working on this. Hello.
What happens if you come and unfold injective?
Oh.
What does he think about A and B?
Yeah, it's fine. We don't need that at all. No, there's still elements of X.
Oh.
And we can keep going, but we still, this is a funny little thing, right? This is a function arrow, but it's also an implication. I've got to come up with a function now that takes a term of this type, which is a proof of this, and spits out a term of that type, which is a proof of that. So hello.
So this thing now give us the fear for something silly. Is there a way for you to say I want this element to be part of that? Just for fun.
You want You want me to? No, every term has a unique type. And no, we can't. Yeah, we can't. I mean, we could.
Are elements of Y.
Sorry?
So I guess it's sort of like something like, can you introduce C and D are as elements of Y?
No, because Y might be empty. X, Y, and Z might all be empty, so it's going to be really difficult to magic up an arbitrary element. And yet, A and B are elements of X. It's like, you're back to being a first year. You're really muddled about what's actually happening. We have elements of X. There's no reason that X can't be empty. This is correct. It's just all logic. I mean, it must be correct because the theorem prover will only let us apply the rules of mathematics. Yeah, so we happen to have some elements of X, but that's only because it was involved in the proof.
Maybe the question is, would you have been able to do anything else than intros?
No, I don't think so. No, I think that's the only first move you can make.
So can it guess that one as well?
Can it guess intros?
Yeah.
No, this is an interactive theorem proof. Let me put H, look, I'll input H as well. There's intros A, B, and H. Now we've got A and B and X, and we've got H as the hypothesis that G of F of A is G of F of B. So now we've got now I want to prove that A equals B. I'm going to prove that A equals B in a slightly quirky way. I'm going to do it backwards, right? So I claim that HF is a function, right? HF is it's not a function in the sense that we would normally think of. I mean, F is a function, it goes from X to Y. But HF is also a function. And what it does is it eats two elements of X, and then it eats a proof that F of them are equal, and then it spits out a proof that the original two terms are equal. So it spits out something that looks like A equals B. That's the output of HF. And so I can apply HF there. And now the goal has changed, right? The idea is the output of this function HF is a proof that A equals B. But unfortunately, that doesn't prove the theorem because we need to HF has got some inputs and we need to put in the inputs. And one of the inputs of HF is a proof that F of A equals F of B. So and then I can apply HG, of course, as well. I spell it right. And now, again, the goal has changed. Now, Lee says you'll be done with this theorem if you can prove that G of F of A equals G of F of B, right? And that's what H says, right? It's not syntactically the same. The H is a proof of that theorem there, and that theorem is not syntactically the goal, but it's definitionally the goal, right? If I do unfold function.conf or whatever it's called, .conf at H. There we go, it's worked. You see, H now becomes syntactically equal to the goal. So this is now exact H. There. So that's the proof of the composite of two injectors. And I don't need this unfold at all, right? You don't need anything unfold. And so what this really is, let me just, let me do that, it's a lambda, right? I'm going to make a function in the lambda character. So this is intros ABH is lambda A, B, and H. Comma, and I'll put an underscore, there we go. And that's a whole, say, haven't quite finished writing my function. I'm now writing a function in what are they called? Functional programming language. This is like Haskell. Lambda ABH comma, this is the output. We're supposed to be proving A equals B. And I said that the way you do that is HF is a function. So let's do HF of something. And now with this goal here, it now says, you know, HF wants to eat a proof that F of A equals F of B, and then it's going to be done. And to make that proof, what do? We do HG of H. There we go. That's compiled now. You see, you can't see there's no red weird lines on the screen. I can get. So that was the proof that we had in tactic mode. I claim that that's a proof that composite of two injective functions is injective. And I think that's kind of interesting because what we're doing is we're saying HF was the proof that we can't see what these things were. If I put the cursor, there we go. HF is the proof that F is injective, and HG is the proof that G is injective. And to prove that the composite of F and G is injective, we compose the proofs. It's literally HF composed with HG is the proof. I thought that was interesting. Anyway, I had no idea that you could think about maths in terms of type thing. So that's what's going on under the hood. We're making functions in a functional programming language. But that's not what I tell the undergraduates. So Right, so okay, how are we doing? We're doing fine. So there we go. We can knock off the proof that there's infinitely many primes in a few minutes. So, and I've already said that, you know, some friends of mine proved that the class group of a global field is finite last year. And so you kind of wonder, you know, that's the kind of thing that we might teach to undergraduates or MSc students. So how far can it go? How far have we got? And we've got a really long way. It's sort of if you look at what's actually been done in lean, then it's like undergraduate level maths, MSc level maths, random, really complicated thing, undergraduate level maths, MSc. That's what it looks like at the minute. So this was a ridiculous challenge that when it was made, but completely out of reach. Maybe I'll click on this. This is my blog. Here we go. Peter Scholzer wrote a guest post on my blog. This was the challenge here. We had to prove, this is the category of condensed abelian groups. This is extension groups in an abelian category. This is an abelian category, and these are, yeah, this is some space of real value measures. This is just some random complicated question. So Scholzer, for reasons I won't go into, you know, that's a talk in its own. Scholzer challenged the entire theorem proving community. It's not just lean, there's loads of theorem provers out there. Challenged us to prove this very complicated piece of mathematics, and we did it, right? It took 19 months from the challenge. We just finished a few months. I mean, I say we. I mean, it was me and several other people, and I was not the main player at all. Here's our, oh, there we go. There's a blog post. I'll let you can read that at your leisure. So this postdoc, Johan Kommelen and Adam Topaz, a young guy in Canada, they were the two key players. So let me show you. Let me not show you that. I mean, this is Scholzer's lecture notes where the challenge came from. Let me search for 9.1. There we go. There's this theorem again. It's expressed as a derived Hom is isomorphic to a Hom. That's the same thing as saying the Hyrex is vanishing. And you look at the proof. I mean, I didn't understand a word of this stuff 4 years ago as well. It was an interesting way of learning this material, is teaching it to a computer. Let me find the proof of this thing here. So here's the proof here. There's the proof that theorem 9.4 implies theorem 9.1, and it's 5 lines long. And there's the statement of theorem 9.4. And theorem 9.4, from where you're sitting, looks just as incomprehensible as theorem 9.1. But theorem 9.4, this is a trivial statement in some sense. I mean, it's not easy, but it's very, very low level. These things are just sort of abelian groups. And this was like lots and lots of maps between lots and lots of abelian groups indexed by the real numbers. This is a very, very low level statement that it only took us a few weeks to formalize the statement of. And only a few months to prove. And then from this low-level statement, you do a bunch of, you look at pro systems of cohomology groups and derived inverse limits. And if you're a research mathematician, you can get from the elementary statement to the hard statement in 5 lines. So as you can imagine, that wasn't what happened with us. So the proof of theorem 9.4 was 6 pages long, and that didn't take very long, really. There's a month. I say it's like a month a page, but you're not just proving the theorem, you're making all the background stuff as well. We had to make the concept of a complex of abelian groups, for example, to get through all this. And then the 5 lines took us a year, over a year. And that's because we just had to make the entire theory of abelian categories, derived categories, homological algebra, and X and Tor groups and things like that. Hello.
This is some of the axiom of choice in it.
Oh yeah, probably. Yeah, we use the axiom of choice without little and the law of exclusion. I've stopped keeping track. At the beginning, I used to keep track. Oh, I wonder if I use the axiom of choice, because that's exactly what you can do. Right? But the answer is yeah, probably. because that's a major. I'll talk about various communities in a bit. But here's the blueprint. So, we rewrote the proof. We rewrote the proof in LaTeX that you could display on the web. And then when you look at these things like this, you can sort of you can jump to the lean code as well. And so you can attempt to work out what's going on. So I should also say, while I was at that, there's some very nice. Let me go back. There's some very nice. Let me show you the nice pictures. Let's get rid of this. There's some nice diagrams. Yeah, these graphs here. These just started off being all white, and then they would go blue when we'd done the statements, and then they would go green when we'd done the proofs. There we go, main theorem there, from the main. So there's the statement of the theorem. You can go to the latex source, and you can go to lead to the lean proof as well. So there's the proof of the theorem. This is what happens when you work with computer scientists. They make lots of nice infrastructure for you. So as I say, it took a year to make it because we had to formalize all of this extra stuff. But of course, now that's made, we don't have to build it again. Right? It's all sort of, the next time somebody asks us some weird question in homological algebra, we'll be prepared. So, okay, I'm going to finish by just giving it some kind of overview of what's actually going on in this area and what people are doing. So there's automatic theorem provers and there's interactive theorem provers. Now this talk is not about automatic theorem provers. There's some examples of automatic theorem provers. There, you ask it a question, typically in a system where there's very few axioms, like you ask it a question about groups and you just tell it the axioms of a group, and then you just leave your machine on for a long time. And it attempts to sort of randomly, it just randomly puts the axioms together in a random order. I mean, it's cleverer than that, I think, nowadays. I specifically highlighted this proof here, the theory in loop theory. A loop is a group without associativity. So these are loops with some property. And the question was, did every loop with some property have some other, did it also have this property here? And because things aren't associative, it's sort of a nightmare to work with. So here's the complete proof discovered by a computer that any set satisfying these 19 axioms also satisfies this theorem here. And the proof is found by a computer. So it's a bit unfriendly. But the most interesting thing about the proof is that it goes on for 1,000 pages. That's absolutely unbelievable. So, I mean, clearly they're not doing things randomly, right? Here we go. There's lemma 2,732. But I mean, the fact that you can come up with 1,000 pages, and I talked to the people about it. I was like, are you sure there's not like a sort of a 10-line proof? They're like, oh no, we have no idea if there's a 10-line proof. There absolutely could be. The only known proof is this 1,000-page proof of this random fact. And anyway. But this is not about, for the remaining 40 minutes, I'll talk about interactive theorem provers. We've just seen one in action, lean. Somebody was sort of saying, oh, can it do the rest automatically? Interactive theorem provers, the idea is you type stuff in, and there's many others, some of which do mathematics, and there's even other systems for which very little mathematics is there, but it certainly could in theory be done. And what are the underlying axiom systems? They're just completely random. Like I was using something called dependent type theory, but some of the other systems use higher order logic or simple type theory. Some of them even use set theory. Remember that? This is the thing that we were all told we were doing as undergraduates. And then there's, some use univalent type theory, which is yet another thing. So basically, it doesn't really matter what the axioms of maths are, they all still prove the same theorems in some sense. And as I say, as well as the 5 or so I've listed, there are many, many more, but what's actually happening with these things is computer scientists are using them to do things which aren't mathematics on the whole, things like program verification. So one problem with there being lots of things is that you would like to take a proof of the prime number theorem in another system and steal it, and so we can have it in our system as well. So that's a very natural question. Can you port proofs from one prover to another? And it's similar to this question, right, which you might know more about. You've got a bunch of code written in one language. Can you magically run a computer program that translates into another? That's the same question, right? And of course, I mean, the answer is people have tried and it's not very good. But actually, do you actually even want to do that anyway? because you would be using C++ idioms in your C++ code, and you would get Python code that didn't sort of take advantage of the Python idioms, probably. So this is a sort of a hard problem. So what do these things do? I mean, they could all be used in theory to prove the class group of a number field is finite. And these systems have been around for decades. And it turns out that it's just not the kind of question that people were interested in. Because the majority of the people working in the area were computer scientists. So in particular, nobody had proved the class group of a number field was finite because nobody defined the class group of a number field. And as I say, this is not because the systems couldn't do it until recently, it's because nobody tried. So it's simple as that. And another example of something I learned as an undergraduate, I learned about sort of the theory of smooth manifolds, but no computer scientist would touch this. Making smooth manifolds are really complicated objects. Making them in theorem proofs is really hard work. So the computer scientists were just interested in other things, so they were doing other things. They were verifying that a C++ compiler was correct or something like this. But then again, should they be interested in tangent spaces of whose job is it to be interested in tangent spaces of real manifolds? That is not the computer scientist's job, right? We weren't interested in this. We as a community weren't interested in the systems. And the computer scientists weren't interested in the mathematics, so nothing was getting done, right? And so this was sort of the thing that what I've been doing since 2018 is trying to say to mathematicians, maybe we should actually start using one of these things. So as I say, now I aggressively market these things because I'm sort of convinced that they're going to change mathematics in some way that I can't really guess, but somehow, in some sense, my main contribution is to get these things out of the hands of the computer scientists who are not really interested in the kind of questions we're interested in. They're typically not interested in elliptic curves or number fields or whatever. But one thing they are interested in is making systems work very well. And if you spend 30 years trying to make a system work very well, then after a while you get the hang of it. There's all sorts of things going on in the background. Problems which have been, I just showed you lead in action. You're like, oh, this looks very easy. Well, 20 years ago, it did not look very easy. It's a huge amount of work from the computer science community to make it look easy. But actually, when it comes to hard mathematics, I'm arguing that it's our job. And who's going to make these libraries? It's got to be us. So I ended up working with Lean. It was just random. Let me tell you something about it. So the source code itself is all free and open source. It's written in C++, mostly by this guy at Microsoft Research, Leo Damara. And Lean 3 was the one that we're all using now. And in 2017, Microsoft complained that people had got them to define groups, rings, fields, and topological spaces in core Lean, but they didn't really need it. They were sort of targeting computer scientists. So they were just like, we could maybe take the groups, rings, and fields out. That was just sort of a proof of concept. So they came out in 2017, and they were put into another free and open source library called Mathlib. So when the library was born, there were 2 computer scientists as maintainers, and there was just random stuff. So I wanted to, use this to do undergraduate stuff, but they didn't have the complex numbers. So my first PR to Mathlib, PR number 21, was me defining a complex number to be a pair of real numbers. So I'd got the hang of it. And there was nothing. There was no vector spaces. There was, it wasn't really clear what the point of the project was. But I somehow was beginning to realise that there was no big, database of undergraduate mathematics. And so I showed up with a bunch of maths undergraduates just goofing around, saying, look what we can do with your software. Look, we've made schemes. And the computer scientists were like, oh, that's kind of interesting. You should publish. It was just like, it was a random project I did just for fun. I was running a club, I still am. I run a club on Thursday evenings, undergraduates come along, and we just do random projects. So we made schemes, and the computer scientists are like, oh, that's never been done, you should publish. But the mathematicians were just like, well, I know what a scheme is, that's not a big deal. So it's sort of funny, mathematicians were wholly unimpressed with the fact that I taught a computer what a scheme is. And so just as a gimmick, we decided to make perfectoid spaces because it was going to be no more difficult than making schemes. I mean, the definition is much longer. We're going to have to make a theory of topological completions of rings, but by this stage, we'd worked out that we'd realized that there was going to be no obstruction. So we just made perfectoid. We didn't prove any theorems about perfectoid spaces. We just wrote down the definition, and then people just went bonkers. It's really, completely, conned the research community into thinking that something exciting was happening. But it was no different to defining a prime number, really. A perfectoid space is just a definition. But we did this thing, and they fell for it hook, line, and sinker. And all of a sudden, research mathematicians started appearing on the Ling chat. And at the same time, I was pushing undergraduates to formalise their lecture notes because I was desperate. You could go off and make perfectoid spaces, but really you want this sort of solid base of like all of an undergraduate maths degree, right? We've got to start with that. And that did not exist in 2018, but by 2019, we had momentum because I'd trained a bunch of undergraduates to type this code in. And they were just typing in their gamma theory notes. It was completely brilliant. So there were maths undergraduates just typing in the theorems of a maths undergraduate degree. There were random research mathematicians who would just like come in because they would notice something funny was happening and, developing harder stuff. People would just start doing, developing the theory. They wanted to they wanted to teach the system the statements of their theorems, that sort of thing. Like not the proofs, because the proofs take ages, but just start by teaching people the statements of the theorems they're working on. And then computer scientists were like, really, they were really a crucial part of the story because we would just get stuck. We wanted to prove theorems about width vectors and sort of reduce to the universal case. And they were like, we can just make a tactic that does that for you, like reduce to the universal case width vector tactic. So they wrote some meta programming code and then we would run it and we could prove theorems about width vectors much more easily. It was sort of really interesting collaborating with these people. And then you kind of think, we should have Dedekind domains. Then you look and you just find some random MSc student that's just made Dedekind domains, proved a couple of basic theorems about them. And then you look back 6 months later, and someone's defined the class group of the Dedekind domain. And then you look back 6 months after that, and you discover that somebody's proved the class group of the integers of a number field is finite. You just put stuff in the library, and then you put some to-dos at the top of your file, and then people come and do it. So right, I'm going to wind up. So it's a gigantic mono repo, Leeds Maths Library. It's nearly 1 million lines of code. It grows to 300,000 lines of code. I think it's one of the biggest projects on GitHub now. I think it's sort of got really out of hand. We didn't expect it to take off like this. And the reason it has to be one repo is because number theories are parasites, right? We use results of, we've existed for 2,500 years. And then these fancy, newfangled theories like topology come along, we just steal them and use them to do number theory. So it's sort of really important that the library covers everything, because you have to cover everything. That means it has to be gigantic. It's written by hundreds of people. I'm one of the people that writes maths. I'm not a maintainer of the library. So I do the advertising. To a small extent, I'm involved in the direction that it's going. But there's many, many people all deciding it's going lots of directions. Obviously, you're welcome to join in. So I'm just going to finish by examples of what's going on. There's a link to the Ling Zulip chat, which is an extremely active, sort of serious research forum. But just to show you the kind of thing that's happening, there's people developing. This is the kind of point, we're at that point now. I have an undergraduate, actually she's now a PhD student developing group cohomology. Got another PhD student developing elliptic curves over arbitrary fields and over number fields. I've got a postdoc developing the theory of local fields. There's a postdoc at UCL. Chris Birkbeck, remember him? Yeah. He's defined modular forms. So there's people just making, definitions and proving basic things about them. There's Ricardo Brasca is leading a project to prove Fermat's last theorem for regular primes. So this is really good. Who cares that Fermat's last theorem is true for regular primes? I'll tell you why we care, because trying to prove that just forces you to develop a good theory of things like discriminants of cyclotomic fields. It forces you to make a good theory of cyclotomic fields and just a good theory of discriminants and factorization So you choose a random project like this, and like at the end of it, you've proved a theorem, but as well, you've grown the library. And Mikhail Stoll has appeared recently. Some of you might know him. He didn't like our proof of quadratic reciprocity, and so now he's developing a new theory, you know, a new proof using Gauss sums. I'm tempted to stop because it's 5 o'clock. I'm not entirely sure I particularly want to say anything else. What does all this say? Yada, 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 yada. Oh, that's an interesting slide. Let's finish with this one. I defined elliptic curves. It was after work with John. I worked with John Cremona 2 years ago, and I started thinking about elliptic curves for the first time. And now we have a definition of an elliptic curve in this sort of this lowbrow way. Y squared is a cubic. And we still haven't proved that the group law is associative because it's a nightmare, right? I mean, especially in this form, just trying to bash out the algebra when you have 5 variables is a nightmare. So we just assumed it's associative and have just pressed on, right? We'll have to prove it at some point. But I have a PhD student who's formalizing a proof of the Moore-Delvey theorem. And I had another student that just a project student, just formalized the statement of the Birch-Smithers and Dyer conjecture. But had to skip loads of stuff, right? For example, they had to skip the proof that addition was associative, but they also had to skip the proof that the L function of an elliptic curve had a meaning for S near 1. And that's going to be impossible to prove, right? You've got to prove Fermat's theorem to prove that. So it's sort of a bit weird. You skip easy stuff and you skip difficult stuff, and I don't know. But that's the kind of thing that's happening in the community now. And yeah, let's skip all that. There we go. I'll just stop there. Right. This. This is the reason I got sucked in, because I just got addicted to it. I would be careful.
More questions? Yeah.
A question about when something is large. Like, I mean, I've seen problems happen with large software projects where some bit of code over here and some bit of code over here, and it's difficult to get to talk to each other for various reasons. You know, there's like for memory management or whatever. I mean, that question doesn't quite make sense here. But
No.
Do you ever have problems of getting different parts of the library to talk to each other, different assumptions or?
No, this is somehow those problems don't make it past the review stage somehow. Yeah, everything is compatible with everything else, and that's the advantage of having this gigantic million-line repository. And occasionally we do things like change definitions. We changed the definition of a group a year ago. Like we just, for some reason, we weren't quite happy with the axioms. So we a definition of a group, we wanted more data. We changed the definition of a group, and then we had to like refactor 150 files. But that's what people take those jobs on.
Yes, so I'm going to ask a really obvious question. What are the advantages, practical, philosophical, what have you, of different systems, say whole life, or beam, for the working mathematician?
For the working mathematician, I'm interested in seeing what happens if we do this kind of thing in several systems, to see which system is best, to see what the advantages and disadvantages. This is the problem we have right now, is that there's only one system where we're building an undergraduate math, even though for me it's the most natural thing to do in the world, is build an undergraduate maths library. If they've got the system, they've got the software working like that, let's build an undergraduate maths library, because that's the beginning, right? But they won't buy it. So, I mean, that's a problem, but that's not what your question is, right?
No, I mean, why are you doing it in Lean and not for light?
It's just a complete coincidence. I chose Lean because random, right? And now we have it, and now the other systems are looking at it again. What's the point of us doing it? They've done it in Lean. We can't get a publication from it, they say. I don't give a monkeys about publications. Right? I'm doing it because I think this is going to change the world.
Well, I mean, I got the sense that say, the whole life community is quite proud of having, not depending on C++ or what have you, depending on a very small, it's the kernel.
Yeah, very small trusted kernel. And we also depend on a very small trusted kernel. But they're not going fast enough. Yeah. They're not going fast enough. But I mean, it's another. Sorry.
Yeah, you talked about converting C++ to Python.
Yeah.
And it's not really useful, but
Could you say take PDF?
really later.
No, I mean, you can convert it. As of 2 weeks ago, the answer is yes, but it probably won't run.
Yeah, surely if someone goes through checks.
At the minute, we've got a new game where you can type in theorem statements in regular math, and it outputs lean code that may or may not compile. But there's an AI using this, it's using GPT-3, using something that was trained on the internet, and also on a bunch of lean code. But it's using machine learning efforts, right? So it might just print out a load of garbage. Yeah, you ask it some weird question about topological spaces, and there's every chance it will actually print out valid lean code at scale. But this is very much on the AI side. And that's only for theorem statements.
So I want to go back to what we're saying, you're hoping this is going to change the world.
Oh yeah, maybe.
Can you say more? Can you?
No, because I don't really like. If I was here announcing that I just invented the CD and say we've digitized music, and that will probably be important. But somehow at the time, everyone's like, well, you know, can you spread jam on them? That was the kind of questions people were asking. You know, would they rot? You know, vinyl we understand, but it turned out that the question wasn't about CDs at all. But, you know, what turned out to be important was things like Spotify that just turned the entire music industry on its head. And I don't want to guess how this will change, how this will turn mathematics on its head. But I do feel that it will. It's just that I don't want to guess how. I mean, I think within 5 years' time, there'll just be some huge database of results in algebraic geometry. And if you're a PhD student trying to read a paper, you know, the author, you know, Deline says this is true, therefore this is true. And you're just like, I don't know why. He's invoked a theorem in algebraic geometry. Let me guess what that theorem is. Then you could ask the system, is this theorem true? And it will either say, oh yeah, it's here in EGA. Or it will say, oh, it's not true, here's a counterexample. I could completely envisage that happening. And then you don't have to type in all the proofs in EGA, right? Just go through typing in, or the Stacks project would be better. Just go through typing in statements of theorems in the Stacks project and statements of definitions that might be wrong, right? Some guy goofs up and it doesn't get reviewed properly. But, you know, then people start typing in proofs and then the mistakes will be found. But you can imagine it being some kind of tool like that. Hello, Andy.
Has a question on Zoom.
Oh. Shall I stop? Shall I unplug something? Or do we have to stop sharing the screen?
No. Hi.
Hi.
Kevin, can you hear me?
I can, but nobody else can.
Oh, okay.
But I'll tell them what you say.
Okay, good. Yeah. Thank you for your talk. So I have one question that you may have addressed a little bit already, and that is about designing an interface for your code, which is important for math software. How much does sort of interface design affect your interactive theorem provers?
So the question was how much does interface design affect interactive theorem provers? And I would say it's been hugely relevant to us, interface design, and that was all done by the computer science people, right? You saw what we had. We had immediate response, for example. Like 5 years ago, that wasn't there. You type in something and you get an immediate response. You watch undergraduates, the immediate response is often, that makes no sense. So it was a game changer having, and also I didn't really show.
Sorry, that's not actually that's. I mean, it's an interesting observation, but it's not actually the interface I meant. I meant more the application interface, the way that you model your data.
Oh, I don't know anything about
the way that you choose your types in this case.
Sorry?
The way that you choose your types in this case.
You're talking about who makes. I mean, making definitions is hard. Is that the answer to your question?
Yeah.
and PRs that make definitions go through extensive reviewing process.
Okay.
Yeah, it's a very difficult question. Whereas proving theorems is cheap. Like once you convince you've got the definitions right, you can prove theorems as poorly as you like, and as long as they compile, they're like great. But if you make a crappy definition, then you're in real trouble because it's really hard to use.
My other question was.
Niels, no one in the room can hear you, so I think it might be better if you talk to Kevin offline.
I'll be here afterwards.
I don't think it's working. I hope you did it this way.
Lots of people on Zoom.
Yeah.
I guess it's because you're using your laptop.
I used a laptop. I'm too modern.
Good. Okay.
Sorry.
So let's have one more from the back and then I think we'll probably it's.
Hello.
So people, the story that you can find schemes,
Uh-huh.
mathematicians in care, and you can find vector spaces,
Yeah.
and mathematicians did care. How did you figure out that was going to be a really effective sales pitch?
Hello. I'm a good salesman. I think it's sort of slightly weird, but it's turned out that I think I'm quite a good salesman. I was constantly asking people, like, I would say to people, would you be interested if I told you that a computer had checked the proof of Fermat's last theorem? And they would just say no. You know, I ask people like Richard Taylor that question, or the students of Richard Taylor. Yeah, and, you know, I really spent a lot of time asking, and also with undergraduates, a lot of time asking undergraduates what they were looking for. And for me personally, I'm sort of driven to make things that other people will be interested in. But there are some people that just, you know, just are interested in making a really big maths brain. It's also independently quite interesting. Yeah, I did a lot of talking. I know a lot of people.
Okay, let's thank Kevin again and all the other speakers.